Hey everybody, it's Jenny from Norman S. Wright. I want to talk about sound today. Sound is really important in buildings. You don't want spaces to be too loud or too quiet. ASHRAE has recommendations for sound levels for different types of spaces, but before we can get into those details, let's just cover some sound basics. So let's get started. So let's start with the decibel. Wikipedia defines the decibel as a logarithmic unit that indicates the ratio of a physical quantity, usually power or intensity, relative to a specified or implied reference level. For our purposes, you don't really need to know an in-depth understanding of the decibel itself, so let's simplify this just a little bit. Sound is a pressure wave. Sound intensity is measured in watts per meter square. The intensity of a sound is different from the loudness of the sound as perceived by our ears. The perceived loudness of a sound is not proportional to the intensity of the sound. It's more proportional to the log of the intensity. This is where the decibel comes in. The decibel is a simple way to compare the loudness of two sounds. Technically, the decibel equals 10 log I over I naught, where I naught is the reference sound of 10 to the negative 12 watts per meter square. So let's move this out of the way and talk about this a little bit more. The important thing to remember is that the decibel is measured against a frequency. The frequency of a sound wave is basically how many times it oscillates per second. Our ears perceive sound differently in different frequencies. For instance, we're more sensitive to high-frequency sounds than low-frequency sounds. We'll come back to this later. There are an infinite number of frequencies, so we group them into octave bands. For our industry, the octave bands are centered around increasingly wider frequency ranges starting at 63 Hertz and doubling from there. So you have 63, 125, 250, 500, 1000, 2000, 4000, and 8000 are octave bands 1, 2, 3, 4, 5, 6, 7, and 8. Octave bands 4 through 6 are the speech interference band or speech interference levels, because most human speech happens between 500 Hertz and 2000 Hertz. Having a sound too loud in these bands could make it hard for people to hear others talk, hence the name speech interference. Different HVAC products generate their highest sound levels in different octave bands. Fan boxes, for instance, have their highest sound levels in the second and third bands, while grills and diffusers create their highest sound levels in the fourth, fifth, or sixth bands. You can often see HVAC data shown in octave bands 2 through 7 because that's where the product's sound levels peak. But in room design, high decibels in the first and 8th octave bands can cause problems as well. I mentioned earlier that we're more sensitive to certain frequencies. For high frequencies, that's about 4th band and higher, the threshold for hearing is about 20 dB or lower. At 4000 Hertz, we can detect sounds as low as 0 dB. But when it comes to the differences in sounds, at high frequencies, we cannot perceive the difference in sounds that are less than 3 dB apart in loudness. In fact, we need about 5 dB difference in loudness in the high frequencies to notice the difference. In these high frequencies, a 10 dB increase would be perceived as twice as loud, and a 20 dB increase would be perceived as 4 times as loud. So at 4000 Hertz, a 60 dB sound would be twice as loud as a 50 dB sound, and a 70 dB sound would be 4 times as loud as the 50 dB sound. Now let's look at the low frequencies. In the low frequencies, third band and below, the threshold for hearing is 25 dB or above. In the first band, a sound would need to be almost 50 dB before we could hear it. In these frequencies, it takes about a 3 dB difference to be noticeable. A 5 dB increase would sound twice as loud, and a 10 dB increase would be 4 times as loud. So going back to our 50 dB example, in the second band, a 55 dB sound would be twice as loud, and a 60 dB sound would be 4 times as loud. Okay, let's move this out of the way because I want to touch on wavelength for a minute. The wavelength of a sound is the velocity divided by frequency. The velocity of sound is 1126 feet per second. So let's look at these octave bands again. Let's draw them down the side this time, 1 through 8. And then let's put the frequencies next to them. And now let's calculate the wavelength of each octave band. So the wavelength of the first band is about 18 feet, the second band 9 feet, then 4.5, 2, 1 foot, half a foot, a quarter foot, and about 2 inches. So now 18 feet, that's bigger than a typical office. 9 foot is about the size of an office. 4.5 foot is bigger than ductwork. 2 foot could be about the size of ductwork. 1 foot is smaller than a lot of ductwork. Half foot is about the thickness of a wall. A quarter foot is thinner than the thickness of the wall. And 2 inches could be the thickness of liner. Now that you can visualize sound waves, knowing how big they are, you can quickly see how some sound waves, low frequency waves in particular, are too large to be absorbed by normal construction materials. So if you take a minute to listen to the sounds around you, you can often hear low frequency sounds of the air handler or fans or fan boxes in the ceiling or even on rooftops, but you can't typically hear diffusers that are more than 10 feet away from you. It's because these higher frequency sounds from the system can be absorbed by the stuff between you and the product in the system, whereas some of these longer sound waves are just too big to be absorbed by normal materials. So let me bring everything else back on screen so you can reference it. So that covers the basics of sound. Don't forget to subscribe to our YouTube channel, and thanks for watching.